All right, so let's actually show you Singularity, the state-of-the-art user interface. Yeah, we're really going to show it.
Wow.
The third time's the charm.
No,
Wow, it looks just like Windows. That's amazing.
I know, we have done it. Mark has done an amazing amount of work. Okay.
Well, you know, if you've got the sort of height of user interface,
All right.
you can't go any higher.
So give you. I'm going to start Singularity up now. What I'm going to do is I'm going to take the second monitor, flip it over. I have a machine down here that has it's an AMD 64 N-Force 4 chipset. Real hardware. We're going to run Singularity on real hardware.
Beautiful.
I can also show it to you on virtual PC, but
No.
It's more convincing
okay.
on 3.
It's real.
So am I going to focus right on in there?
Yeah. Okay. So
Okay.
I'm going to go ahead and let's see. I got to do all this in order, just so I get the boot right. All right, hold on. Oh, I turned it off. There we go. Okay. Now the machine's starting up. Okay, and we're going to network boot Singularity. It's actually the way we normally run it in our environment is network boot. Because we can repurpose the machine and recycle, and we don't have to re-image the hard disk drive or anything else.
Okay.
And then my desktop PC on the left is actually running a boot server. Okay, so we've loaded in the bootloader. It's now loading in the kernel and all the device drivers and bringing them in over the network. Okay, we also support hard disk boot, CD boot, and boot off of a USB device.
Nice.
Okay, like a memory stick.
Mm-hmm.
Okay, and let's see, it's come up. Okay, we're almost up. So you can see it's saying, hey, we're running a kernel written in C#, and it was compiled. I actually compiled it while we were having the earlier part of this discussion. Built the system from scratch. And here it is, the state-of-the-art in user interfaces for Singularity, okay?
Oh, right.
As good as you could get.
Nice.
Pay no attention to the fact that it looks like DOS.
This is back to the old 89 or 90-10 rule, right? Okay.
Yeah.
Let's see, wrong keyboard. I'm going to use the right keyboard. Okay, so I can do a directory and see this is my local memory-based file system, and I can see all my apps that I have installed here. I go look at the dev, and I can see the devices that I have here. Let me tell you a couple of the user interface features. So one of them is this green bar across the top, and you'll notice it's moving pretty quick because we're scheduled. But there's I don't know, it might even not show up on the video. But there's a yellow twiddle that
I see it.
across. Okay. Yep. What this is showing is which thread. Every time we schedule a new thread, we move the twiddle one character forward, and we draw a different character for every single thread. Okay. The system is very heavily threaded. We have tons of threads in here, and we have a lot of processes. In fact, I'll do a task list here. Oops, if I could spell. And I can see the processes that are running. So I have the kernel is running, the idle process, which is just if no one else is running, the volume manager, which knows how to take a disk and split it out into volumes. I'll go through, so you can see there's a process for each device that's running. So if I have 2 disk drives on this machine, so I have a separate disk driver up and loaded, separate disk drive process for each one. I have the keyboard. The NVMac is the network interface card on this machine. The network stack, I have a ISO 9960, so the disk drive or the CD file system. Boxwood is the network or is the disk file system. Okay. And then I have a TTY. I have the shell that I'm actually running on tasks. So you can see each one of these is a separate process. They're running completely
in a SIP.
Each one of them is running in a SIP.
And we talked about the microkernel design and how Singularity looks a lot like a traditional microkernel in the sense that things like drivers and like the file system are broken out into separate processes.
Yeah.
And I think that far right column here tells that you're running in the default configuration where everything's in the same hardware protection domain.
So this
everything's in number 1.
So we're all in one
that's
hardware
what you've
protection.
done.
And the fun thing about Mark's hardware protection implementation is that we can do it. It's an install time. Well, actually, it's a runtime decision. So we can, if I can reboot and say, okay, next time when I reboot, I want the kernel its own domain and everything else in separate hardware protection domains.
Excellent.
And just get it.
But let me ask this question just quickly. What happens when my SIP, and I'm a developer, and I've written a loop that I made a mistake in my code that you guys didn't catch, because you're not going to know necessarily that I'm writing a loop that's going to run forever because I don't know what I'm doing.
Yeah.
Then what aspect of the system says, I have an out-of-control SIP here?
Oh.
Kill it.
Well.
So what's the global watcher?
Oh, okay. So you talked about two different things. So one of them is, just... Okay, so we have preemptive scheduling, for example, right? So we'll just interrupt the processor, we'll interrupt that thread, and we'll run other threads, and so...
So you can't just stop the system. You
And
can't bring the system to a halt.
then I can just do a kill. Let's see what happens when I kill 8. Oh no, we didn't call it kill. What did we call it? Dang it, I can't remember. There's some command that I can't remember the name of.
Fine. Well, you're a kernel guy. Huh?
Yeah, I am a kernel guy.
Look at this silly UI. You don't play with this stuff.
So the question is there some system at the top watching all the thread processes? And there isn't yet. This is one of the things we're building.
Okay.
In fact, it's what Mark and his intern are working on this summer is the service manager that watches everything else and decides, that thing doesn't look like it's behaving the way it ought to.
But how do you watch everything else? How do you get into another process?
Well, the thing
when you have an isolated system like you're talking about.
Well, the kernel knows what's happening, right?
The kernel does know.
The kernel knows, and the kernel does know. For example, one of the key aspects is: are you communicating, right? Because a process that's run amok, typically, it's going to go into itself and get stuck, right?
Okay.
And so we can look and see, is communication flowing across the channels at the rate that we expect, and if it's not, go shoot the thing in the head, and start up a replacement.
Excellent. Okay. And that's just another component you're putting into the kernel, and
I think it's fair to say that our overall goal is, a reliable system that has predictable, well-known properties, and we've sort of walked before we could run, right? The project's been running for 3 years or so, and we started with these sort of fundamental questions of how do you build software for the system, what languages are you going to write it in, what properties can we verify, lots of sort of static things. And this summer is sort of an interesting time to be on the project because, and more recently with software as a self-describing manifest and annotating the device drivers, we're slowly sort of moving our way up the food chain, right? So now the questions that we're worrying about are, okay, we have a booting system, it's got these SIPs, they have interesting properties, what if they run amok? We haven't caught all the properties, what if they start to misbehave, can we shut them down and restart them? So, we've gone through this in order. We've established hopefully a firm foundation with these static language-based techniques and verification, and we're moving on to what the system looks like and behaves like when it runs, when it executes.
Cool. Excellent.
So I want to show you one more piece of the demo.
Please do.
This is just to bring home the fact that it is a compiled system. So I'm going to type, we have a special command called break, okay? That what it does is it stops the system and drops us into a kernel debugger. I'm going to have to turn off this display to get my keyboard and mouse. But we come over to the machine on the right, and I have anybody who's written, say, a device driver for Windows will recognize this program. It's the Windows debugger. Okay, the Windows System Debugger.
Sure.
And let's see. Let's start the stack. Anyway, we have full debugger support for WinBag in Singularity, okay? So I can actually go in and I can see, so I've broken in the shell, there's a break, and you can see everything that's in the stack. So, and I can go in and let's go in and look at the main, and I can pull up source, and I can debug this just with a standard debugger. And let's see, I can go look up local.
And look at that.
Okay, so not only have we shown you a demo, we've actually shown you authentic Singularity source code.
Wow.
Okay.
Unrecognized action.
All the way down to
excellent.
The startup. Here's the let's see. Here's the startup code for starting up a process. Okay, and a thread when I start up a thread inside. Okay. And
very cool.
And it's just compiled code, so we actually didn't have to. We had to teach the debugger about Singularity, that its processes are different than Windows processes, a couple things. But we didn't have to teach it about safe code versus unsafe code, because to the debugger, it's just compiled code. It just looks like C++, it's only C#.
In fact, we have a sort of mangling transform, right? The C# names get sort of mangled into pseudo C++ symbols so that the debugger will understand them.
Well, this is great. So real quickly, because I know you have work to do, and they probably want me to get out of here and taking up valuable mind time. What do you foresee for the next 6 months, Singularity? Like, I mean, we're going to be working on this. Like, can you talk about that? Like, what kind of...
Ask Jim first, and then
Ask Jim.
and then we'll come around to the rest of it.
I'm trying to get away.
Camera should be.
The door's locked.
Doors locked. So, I think Mark's already alluded to some of the interesting things we're doing. We've got a basic system running, like Galen showed you. We've been measuring some of the performance of the basic core system, and now we get to do the really fun stuff. Now we get to start moving up the food chain and start talking about the higher level problems that we're trying to solve with Singularity. So we've done some work on verifying parts of the system. We're doing work on security. We have a new security model that we're building. We're going to do some work on installation. We would really like the installer to be a little bit big, more general and robust, not just device drivers, but also applications. Mark's been looking at building the resiliency into the system to recognize when things have died and to restart them so that the system after a failure has a hiccup but doesn't sort of come apart and stop running.
Mm-hmm.
And so we're trying to move up that level. And then in terms of the language level, there's lots of things we want to do to verify the code. We've been building tools inside MSR for quite a while to do verification. There's a very interesting project called Spec Sharp, which has added pre and post conditions and object invariants to the C# language, and we use that language as our language, but we really haven't taken advantage of it yet. We would like to go in and try some of that specification there so that we could apply some of the tools they have for checking the specification statically. We have a very powerful theorem prover based technology that allows us to find some errors in the code by checking it. We've also mentioned transactional memory.
Mm-hmm.
We've implemented some of the Singularity processes using transactional memory. We're trying to get some other applications going that are written using transactional memory, so we'll have more test cases for Singularity and more experience using transactional memory to write application code.
Cool.
So we got a lot of stuff going on.
Absolutely.
The other two things I can think of to add in there, we're doing some work on the multi-core. So what if you have in fact what Intel likes to call many-core. So if you have a machine with 1,000 processors on it, what does it look like? You probably don't want to run a complete copy of the operating system on every single one of those processes, for example.
Sure.
Okay, and so we're doing some work there. And the other area I can think of that we're doing work is in terms of trust between processes and the system. So if I'm a piece of code running on the system, how do I know that I haven't been tampered with? Mm-hmm. So a good example that people like of this is these large multiplayer distributed games, mm-hmm. and people will go in and hack the local copy on their machine and cheat.
Attacked unfairly,
and so you could secure that and be able to say do I trust this process or do I not? So those are some of the other things we're working.
Sure. Now, but just real quickly, from the multi-core standpoint, when you guys on your lowest levels, you're using unmanaged code to handle the locks and your typical kernel type code, right?
Yeah.
I mean, you're
so interrupts, incoming interrupts.
Bottom of the kernel.
Very bottom of the kernel.
Yeah, yes. You have to do that. Right?
But we're not talking about very much code.
Yeah. Okay.
Hundreds of lines.
Yeah.
Maybe.
Okay.
Yeah.
But there's no way for it to be fully managed at some point. You need managed hardware.
Well, no, that's not true because we compile things, right? So it's a matter of making the languages, the higher level language is expressive enough that they can express the capability, the very low level hardware things. And this falls into some work that the typed assembly work that I already talked about. There's an extension of adding in additional support.
Yeah, let's take what I said.
Very cool.
People are trying to write system components. People in our group are attempting to write system components like garbage collectors, which are sort of the preeminent example of, well, here's something that intrinsically has to manipulate pointers to memory and decide to free objects and stuff like that. It's thought to be possible. In fact, I think there are examples of writing simple garbage collectors in a completely type-safe way.
Excellent. Well, I look forward to Singularity 4.
Yep. We'll be back.
We made so much money from the previous movies.
Fantastic. Well, thank you guys. It's
thank
always
you.
a pleasure to chat.
We love the Channel 9 audience.
All right. Well, they're going to be really psyched to have a new Singularity on C9. They've been asking for it.
Great.
So.
Oh, very good. We're happy to accommodate them.
Yep.
Cool. And nice to meet you as well. Great job. And we'll come back again. We'll see you and see what you found out about this on the higher levels. Thank you.
Thank you.
And not doing it.
Well, they're going to be really psyched to have a new Singularity on C9. They've been asking for it.
Great.
So-
We're happy to accommodate them.
Yep.
Cool. And nice to meet you as well. Great job. And we'll come back again. We'll see you and see what you found out about this on the higher levels. Thank you.
Thank you.